Now that we've talked about shear force and we've learned a little bit more about rod ends, we can talk about the way they're supported when we install them. There are two ways of doing this, which are referred to as single shear and double shear, and it's sound engineering practice to ensure that we always use double shear where possible. Let's dive in a little deeper and learn what each of those terms mean. Single shear looks like this, where the rod end is bolted to a single bracket. The downside of this is that if enough force is applied to the rod end, the bolt will fail in shear. Essentially, it'll be cut in half. On the other hand, if we added a second bracket on the other side of the rod end, we now have double shear. In this case, we'd be able to apply double the load to the component before a shear failure occurs, even though we're using the same size and material for the bolt that attaches to the rod end. As well as the increased strength that double shear offers, it also means there's no bending load being applied to the bolt and the mounting bracket. If we consider again our single shear installation, any load being placed into the rod end here will do so through the centre of the rod end. Since this is offset from the bracket that the rod end is bolted to, it'll have the effect of trying to bend the mounting bracket. If the material strength is marginal, this can result in the bracket or weld between the bracket and the rest of the chassis failing over time. Even if a failure doesn't occur, single shear will result in less stiffness and more compliance than a double shear installation. Double shear is usually easy enough to incorporate when we're considering the way something like a suspension arm attaches to a chassis. We simply need to ensure that we include a mounting tab on each side of the rod end. However, we also need to make some allowance for the movement and angulation of the rod end. If we literally clamp the rod end directly between two brackets, then we'd severely limit the angular misalignment that would be possible before the rod end ended up contacting the bracket. To get around this, we'll usually see that the gap between the two support brackets is significantly wider than the actual rod end width, and the extra width is then accounted for with machine spaces on each side of the rod end, and the bolt will then run through the centre of these spaces. This also means that we don't necessarily need to use a bolt that has the same diameter as the inside of the rod end. Instead, we may perhaps use a 5/8 inch rod end, which means that it has a 5/8 inch diameter hole through it, but we can use a 1/2 inch bolt to attach it. We can then account for the difference between the outside diameter of the bolt and the inside diameter of the rod end with the machine spaces. Usually, these spaces would start out with perhaps a 6mm wall thickness, but then taper on an angle as they approach the rod end to allow for maximum angulation. These spaces can usually be purchased from rod end suppliers to make our job easier, but if you need something a little more specific, then any machinist will be able to easily machine something to suit your requirements. Where double shear can become a little trickier to incorporate is in the way the suspension upright attaches to the suspension arms and the steering tie rod. Usually in a production car, the ball joints at these locations will be installed in single shear for reasons of manufacturing ease and cost reduction. Of course, the engineers designing these components understand the forces involved, and the ball joints are suitably sized to ensure safety and reliability. Where we can get into trouble though is when we start modifying the suspension geometry. Take for example a situation where we want to correct the roll centre height on a McPherson strut front suspension, which is a common handling modification for a lowered car. The specifics of the term roll centre doesn't really matter, but what it means is that the outer ball joint is spaced down from the attachment point on the strut. If you've been following along so far, you'd hopefully have picked up that this is going to place a significant bending force into the ball joint and the spacer compared to the factory installation, and in fact, the more we lower the ball joint, the worse this situation gets. This can be potentially dangerous, and there have been plenty of instances of suspension modified in this way failing in use. Even if a failure doesn't occur, the bending load is almost certainly going to result in some amount of compliance in the spacer when it's arranged like this. A similar situation occurs if we look at the way bump steer correction is handled. This is usually achieved by spacing the steering tie rod up or down from the steering arm that attaches to the hub. Not only does this place the bolt that attaches the steering tie rod in bending, but it also adds torsion to the steering arm, which can again introduce compliance into that part too. While it's difficult to really fix this situation in a production upright, if we look at how this is handled with a dedicated motorsport upright, things are very different. These are designed so that an enclosed spherical bearing in the suspension arm can be attached to the upright in double shear. By adjusting the thickness of spaces placed above and below the spherical bearing, the same effect of adjusting the roll centre can be achieved while still supporting the arm in double shear. This particular upright is actually designed for a double wishbone suspension design, and we can see that it offers the same double shear arrangement to support the top wishbone as well as the steering or toe control arm on the side. So the key point to take away from this module is that whenever possible, we want to ensure that our rod ends are supported in a double shear installation. This may not always be possible when modifying production parts, and in this case it may be necessary to compromise the geometry we're trying to achieve, use oversized parts, or both in order to ensure safety and reliability. That was just one module from our Motorsport Fabrication Fundamentals course. If you're interested in learning how to fabricate components for your vehicle, then this course is going to be perfect for you. You will start by learning about the various tools that you're going to need for motorsport fabrication, as well as how to use them. You'll learn about techniques such as bending and notching tube, drilling and tapping holes, and how to use dimple dies. You'll also learn about MIG and TIG welding, which are both popular techniques for welding in the world of motorsport fabrication. While you don't need to be a mechanical engineer or have a degree to fabricate parts, you'll also learn some fundamentals of design so that you're able to design and fabricate strong and reliable parts. All of this knowledge is then tied together with a range of worked examples so you can see how these skills and techniques are put to use with real-world fabrication projects. If you're a motorsport enthusiast and you want to expand your skill set so that you can start fabricating parts for your vehicle, our Motorsport Fabrication Fundamentals course is perfect for you. If you'd like to find out more about this course, click the link in the description.